Welcome everyone to lesson 1.9 of Precalculus, which is all about rational functions and their vertical asymptotes. So let's get started. So before we officially dive in, I want to just introduce this vocab word of one-sided limits. So before we would look at as x approaches something, what is the y approach? This time we're going to look at as the function approaches this x value from the left or right side, what is the value of the function approaching? Essentially, when a function approaches two different values at the same x value, that limit doesn't exist because the two sides are going in two separate directions. With a one-side limit, we're only focused on one side, so we don't have as much restriction with it. All right, so we can already tell from this function it's defined graphically that its vertical asymptotes are at -5 and at +2. So x equals -5 and x equals 2. So if I want to describe the behavior of the function around these vertical asymptotes, I have to use what's called a one-sided limit. And if we notice, the x is approaching a number, but that number has the exponent of negative or positive. Negative means it's coming from the left, and positive means it's coming from the right. So the notation is a little bit weird, but there's a little bit of sense to it. We're going to focus on the -5. So as the function approaches -5 from the left, it's going down forever. So that would be -infinity. And as the function approaches -5 from the right, it's going up forever. So that would be +infinity. So not too bad. Unfortunately, it's a lot more writing for the limits, but it allows us to describe the behavior of asymptotes when they go in opposite directions. So let's continue. We have this function here, and we're not given a graph. Super scary. We want to state the vertical asymptotes using limit notation. Well, let's factor this sucker. We get x minus 3 times x plus 3, and then x minus 2 times x plus 2. So we get some zeros and asymptotes to work with. We get 3 and -3 for zeros, and 2 and -2 for asymptotes. So we know from the function itself that we have zeros at -3 and +3, and we have asymptotes, I'm just going to draw vertical lines, through -2 and +2. But we really don't know what the rest of the graph looks like. So for us, we can plug it into y equals or plug it into Desmos, and we can pick some points, we can plot some points. Or if we didn't have a calculator, we could just pick some x values and plot some points. But we should end up getting some nice points of 1, 2, -1, 2. So we get some nice behavior in here. Oh, it just likes to move. So this side is going up like this. We have like a nice U shape here. And then this one, we can tell it has a horizontal asymptote at 1. So I'm just going to draw that here. And we'll have this nice behavior here. Now I drew it all in the same color because I am not very user-friendly. So what we can do is we can actually change the color of these to, let's go with purple, or just any color if we want, really. I'll pick purple just because it makes life a little easier for us and easier to see. So we get this nice red function. Now the question wants us to state the vertical asymptotes using limit notation. So we have 2 of them, so we're going to have 4 limits. So we're going to have x equals -2, and then x equals +2. So limit as x approaches -2 from the left. From the left, we are going down. So g of x is approaching -infinity. The limit as x approaches -2 from the right for g of x, that is going up. So that would be +infinity. +2 looks to be the opposite. The left is going up and the right is going down. So our limits should respect that. So left, g of x is approaching +infinity. And the right would be -infinity. So not too bad. Just each one has 2 limits, kind of like a horizontal asymptote has 2 limits. A vertical asymptote is probably going to have 2 limits as well. So just to reiterate, vertical asymptotes occur in rational functions when the zeros of the denominator are either not zeros of the numerator or they have a larger multiplicity in the denominator. So if negative 2 is a 0 in the numerator once and in the denominator twice, even though they have it in common, since the denominator wins out, it's going to be a vertical asymptote. So that'll come into play a little later, I believe. Maybe not today, but later on. So one of my students pointed out to me that I did this wrong the first time I recorded it, so here is my attempt number 2. So to find a vertical asymptote numerically, we need to use our calculator. So the first thing that we're going to do is we're going to verify that we actually do have a vertical asymptote with this function h. So I'm going to factor it. The numerator will be x times x plus 3, and the denominator will be, well, just the x minus 2. That doesn't need any factoring. If we look for what makes the numerator 0, we have 0 and negative 3. What makes the denominator 0 would be a 2. Since none of those are in common, the 2 in the denominator is a vertical asymptote. So let's see what directions everything goes in. So if we're going to approach 2 from the left, we need to use numbers that are to the left of 2. And we're going to get closer and closer and closer to 2 as we go. And we're going to see what happens to the values of h, what's being outputted. And the direction that goes tells us if that side of the function is going towards positive infinity or towards negative infinity. And conversely with the right, same idea. We're getting closer to 2 from the right and seeing what happens there. So let's turn on our calculator. And what we're going to do is we're going to go to the y equals screen. And we are going to type in our function. I'm going to type in the default one. I'm not going to modify it. So alpha y equals will get us a fraction here. And we're going to do x squared and then plus 3x. And denominator is x minus 2. And there we go. We're going to make sure our calculator is formatted properly. So we are going to go second table set. And remember that we want the independent on our table to be ask. This allows us to input values. And we're going to double check the mode and see that everything is as we want it. Something I found out recently is this graph table option. So let's try it out and see if it works in this. So we're going to go to second graph. Brings up the table. And the cool thing now is I get to see part of my graph here in addition to my table. So we can actually zoom out with the graph, and that might help out a little bit. Let's do that. So let's actually zoom out. So we'll hit zoom. Zoom out is 3. So not great. There we go. So now we can see the graph and how that's going to look. So we can see graphically that the left side is going towards negative infinity and the right side is going towards positive infinity. So let's type in our numbers and see that numerically. So we're going to hit second graph, and that allows us to bring up our table. And we're just going to type in these numbers. So we're going to do 1.9, 1.99, and we're getting closer and closer to 2 every time we do this. There we go. So we can hover over those y values to get a little bit more detail. So we see from the 1.9 that we get a negative 93.1. Then we get a negative 993.01. We get negative 9,993.001. And then, so this notation here basically means a really, really small number, or really, really big number, my bad, really big negative number. But we can see there, like, it's negative 99,993. So this is just a really big negative number, or a really small number, depending on how you want to view it. I'm going to say a big negative number. So as the x gets closer and closer to 2 from the left, we're getting larger and larger negative numbers. So limit notation, how do we write that? Again, limit of h of x, because that's what our function is called, as x goes towards 2 from the left, is negative infinity. And again, we can see that graphically by going towards 2 from the left-hand side. We can see it's going drastically down there. There's a lot of distortion down. On the right-hand side, well, we can change our numbers to 2.1, and then 2.01, and then 2.001, and then finally 2.0001. What do we get this time? We get some big positive numbers. We get 107.1. We get 1007. We get 10,007. And then, what is this? This is 100,007. So a big positive number. Again, we're not worried about like the specificity of these numbers. We're worried about what direction it's heading in. And again, as x gets closer and closer to 2 from the right, it's going towards positive infinity. We can see that graphically here. How do we write that? We want the limit as h of x as x approaches 2 from the right is equal to infinity. So that is my fix. Thank you to my student for bringing it to my attention. And here's back to the rest of the video. So let's look at this function analytically, and I do believe it is our last one here. And this one is where we have some multiplicity concerns. So the reason I mentioned the one above. So if we factor this, we get x plus 6 and then x minus 2, which means that negative 6, positive 2, and then positive 2 with a multiplicity of 2 for the denominator. So the only thing that makes the denominator 0 is positive 2, so our domain would be negative infinity to positive 2, and then positive 2 to infinity. But we don't have a whole, because the multiplicity of the denominator wins out. If I cancel this, you want to think about it that way. If I cancel out the common factor, it's equivalent. This function is equivalent to saying we have x plus 6 divided by x minus 2. And since we still have that x minus 2, that's why we have a vertical asymptote and not a whole. So there is no whole. Our 0 would only be at x equals negative 6. That is not a 6. Our vertical asymptote would be at x equals 2. The limit notation of our asymptotes, well, we kind of need to figure out what's happening here first. So this is where we're going to plug in values. H of 1.999 is equal to negative 7,999. So the left is going down. Might hope if I could spell it. And then h of 2.001 is equal to 8,001, which means the right is up. So to write our limits, the limit as x approaches 2 from the left of h of x, left is down, negative infinity. The limit as x approaches 2 from the right of h of x is going to be equal to positive infinity. Horizontal asymptote, we have the same degree in the numerator and denominator, and the leading coefficient would be 1 over 1, so that would be y equals 1. So our end behavior, anytime it asks for end behavior, we're going to tell what that is in limit notation. So the limit as x approaches negative infinity for f of x is, oh, I did h here, whoops, is 1, and the limit as x approaches positive infinity for f of x is equal to 1 as well. Remember that if the degree of the numerator was larger, we would have infinite end behavior, and we would have to plug in a negative really big number and a positive really big number to understand what's happening there. Other than that, that is pretty much it for this lesson. If you have any questions, please make sure you ask in class. Otherwise, I'll see you in the next lesson.